Okay. Hey, everyone, and welcome back to this week's seminar where we talk about ML protein engineering. This week, we're really lucky to have Zaixiang, who's going to talk about diffusion language models. So just a quick bio about him is that he's a senior research scientist at ByteDance. His research interest lies in large-scale generative modeling and applications in various real-world problems, especially in human language and AI for science. At ByteDance Research, he's working on generative protein modeling and design affiliated with the AI drug discovery team. And before that, he received his PhD in computer science from Nanjing University. So I will hand it off to him now. He has asked if there's clarification questions. You can leave them in the chat, but if there are more discussion questions, that we reserve them till the end. So feel free to just put those in the chat until then.
Yeah, thank you, Rhea. Am I pronouncing right? Thank you so much for your kind introduction and having me here. And I'm Zaixiang. I'm from ByteDance Research, and I'm very happy here today and sharing our recent work about combining the diffusion models, discrete diffusion model and language model for protein language models. The two driving forces of the recent generative AI, and our work is titled "Diffusion Language Models are Versatile Protein Learners," and which has been accepted to SML this year. And this work was done with my excellent collaborators, especially our intern Xinyu from Nanjing University, and my colleagues Dongyu, Zhouyi, Fei, and Shujian and Chen. And we are from AIDD team at ByteDance Research, and it stands for AI for drug discovery, and we are doing some fundamental research for AI research for drug discovery, especially for proteins. And here is three main topics we are pursuing for AI for protein modeling and design, and for small molecules designs, and cryo-EM reconstructions. And as a quick highlight of our recent work, and the first one is ion design. In this work we use to repurpose large pre-trained protein language model to design sequences for given structures, and for this is the work I will cover today, and to develop a protein language model that can both understands and generates proteins. And we also develop energy-based preference optimization framework for designing antibodies with higher affinity. And we also do some small molecule design with decomposed prior for diffusion model. And as for protein conformation generation, we in this year's SML we introduced the physics-guided diffusion model to generate conformation ensembles, and we also focusing on cryo-EM heat reconstructions with deep generative models. And okay, so this a very quick record of our introduction of our team's work, and let's get started to today's content. And yes, so as I said before, today's topic for our work is focusing on developing a new kind of or new generation of protein language model that can do both generation and representation learning for predictive tasks, and deep generated models, and which has we can see a lot of amazing thing, and during these days is come from like deep generative model. For example, like use diffusion model to generate new images, or like large language models to act like a human parroted. And the core idea of deep generative model is to learning to generate data, and it's a famous quote from Dr. Yang Song, from his famous paper. And creating noise from data is easy, and creating data from noise is generative modeling. I think this is the best description of deep generative modeling. And like for the protein data we are interested in, generative modeling for protein data, especially for the two major modalities, the protein structures and protein sequences, has gained a lot of interest during these days. And there are increasingly many recent research papers on these topics, and the diffusion model and language models are the two cornerstones to this generated paradigms for like modeling protein data. And we can if we when we are talking about protein data, there are two major modalities: the structure and the sequence. You can see from these slides. And if we like these two modality we can like to describe their mapping from each other, or like a generation from noise to generate any kind of any one of this modality, or simultaneously generates both this modality. And this established like 4 tasks, or 4 generated tasks of like generating protein data. For example, the protein folding is to generate protein 3D structure from amino acid sequence, and the inverse folding is to generate amino acid sequence condition on protein 3D structures. And when you and you can also like unconditionally model the protein sequence or protein structures, and you can get a model to you can do like de novo sequence design or de novo structure design. And ultimately people want to like doing to achieve a unified model that can like co-design or like co-generation of these two modalities that can like the best describes the protein data you want. And today's outline is like we will organize. I will organize my presentation in the following structures. And the first way I will slightly call back the generative model for proteins, and then I will talk about the current paradigm of protein language models, the pros and cons, and what we really need for the next generation of protein language models. And after that, I will introduce our answer to these questions with our proposal. And diffusion model, and we know that there are two like very popular generative model. The one is diffusion model, and the diffusion model. Today I will not get into very detail of the mathematics aspect. I will try to give more insights about how to like use this like generative modeling to learn and generate protein data. So like for diffusion model, the philosophy behind diffusion model is to generate by iterative denoising from noise. And you can like start with a completely noise and an iterative denoise, or like add some like signal to the noise, and then after like many steps, you can get a like clean data, which is the sample you want. And you learn this diffusion model by like a forward process using like a clean data, and you add noise to the clean data, and you learn to denoise from this clean data, this noisy data to the clean data by learning to reconstruction. And then when you get this like denoiser model, and you can use in the inference and to like start from a completely noise states. And these popular paradigms like it works very well in many scenario and area. For example, for like images and or videos, or especially it also works very well in like a protein structure. And like for protein structure, the if you can say the only foundation, I can say it's like the folding model, and everything, the story starts from the AlphaFold, and we can regard alpha folds as a sequence or sequences condition or MSA conditioned structure generation model, and it has a it takes as input the protein amino acid sequence, then give a black box model, kind of like a transformer, pairformer, or evoformer, something like that, and generate protein structures. And you can see that for like the for AlphaFold 2 and AlphaFold 3, and the generation process, it's something like a recycling or iterated denoising. In AlphaFold 2, you will recycle. You will recycle the structural module for like several iteration to make the prediction better and better. And it's kind of like this denoising process is very similar to the diffusion model. And in the latest version of AlphaFold, they replaced the structural module from this naive recycling manner into a like generated generalization of this iterated denoising into a true diffusion model. So for protein structure data, the best or the best performed model today, or generative model today, is powered by the diffusion model. And so we can keep a briefly summarize of AlphaFold. AlphaFold is like it's a sequence conditional structure generation model with a transformer as the neural network parameterization, and with retrieval augmented generation from like from MSAs, and diffusion model as the generative protocol. And this is the sequence conditional structure generation model, and we have diffusion model for like completely unconditional structure design, or we can also introduce other constraints. One of the notable pieces of this line of work is RF diffusion, and in RF diffusion, they repurpose a pre-trained sequence conditioned folding model to a unconditional backbone diffusion model, and can like attend impressive wet lab experimental results and design many like designable proteins in the lab, and you can impose many constraints into the generative process to like realize your desire into the designing process. And so as we can see, like for protein structures, we have like diffusion model is the by default the powerful generative paradigms to learn it. And like for protein sequence, and because the sequence protein amino acid sequence is the sequence data, so many like people from machine learning or NLP area, they inspired by the recent advance of the language model. They because there are a very similarity between the protein amino acid sequence and natural language sequence. So language model can be used to model protein sequence, and the widely used language model in NLP is autoregressive language model. And the autoregressive language model generates data element by element. And if you have like a structured data or sequence data, you generate data with a predefined order, and then generates data and learn data element by element. And you also have for protein data in particular, you have like ESM, the evolutionary-scale modeling. It's like a BERT model for proteins, and it learns with, it's not a autoregressive model, it's like a mask language model. And the mask language model is more often to serve as a sequence encoder or embedder to provide learned repetition for downstream predictive task. The mask language modeling is tasked to reconstruct the mask amino acids and to the ground truth amino acids. But the masking ratio is a fixed ratio of like 15%, and they learn from like a lot of evolutionary scale sequence data, and can learn the evolutionary pattern inside the sequence data, and can use this learned evolutionary knowledge for downstream tasks. And we also like have like a GPT like autoregressive model for protein sequences. For example, like ProGen is a autoregressive protein language model, and you can impose condition as a prefix or tag before the sequence. You can import a tag here, and you can which relates to the protein superfamily or protein family, and in inference you can use this tag to generate a protein sequence of a specific protein family. And yes, and so the ProGen model generates protein sequences is very likely to ChatGPT kind of autoregressive language model. And like for mask language models, and researchers from Meta, they verified that scaling this kind of language models can make things different. And you can, when you're scaling the model, you can better learn the information or context or knowledge inside the larger amount of sequence data, and you can use this like learned pre-trained protein language model to do single sequence structure prediction, and you don't need to retrieve the multiple sequence alignment, and can attain a reasonable accuracy in comparison to AlphaFold. So the success of these two paradigms, the diffusion model for proteins or the language models for protein sequence, the hero is the transformer, and the transformer is a scalable and strong learner for structured data like protein or like natural languages. Because the reason behind this is that when you are stacking like the core component, the attention of transformer, you're stacking layer by layer, multiple layer. You are approximating the statistical dependencies inside this structured data, because and for protein data, this statistical dependencies corresponds to the like residue-wise structural physics interaction or the co-evolution patterns of like two amino acids. And so we have like pretty much covered the widely seen generated paradigms for protein data, and we pay special attention to the protein language modeling. And when we like look into the protein language modeling, and as we said, there are two kind of protein language modeling, and the one is mask prediction, and the second is autoregression. And we are arguing that these two kind of widely used learning objective is not necessarily the best objective or best paradigms for learning protein sequence data, because for example, for mask language modeling and you have like ESM, which have like very good performance in understanding protein sequences for in various predictive tasks, because they have like bidirectional receptive field. They can like fetch information globally or like from the whole sequence. But the mask language model like ESM cannot generate protein sequences. It's not a generated model. It lacks of a well-defined formulation for generation, and we argue that this could like further harms the predictive power of this kind of mask language model, because in mask language model you learn you mask the protein sequences for a very small ratio, like 15th proportion of the sequence to be masked, and this is a not that challenging task. And when you want to, for example, to get a very good predictive power or very good representation learning model, you want a sufficiently challenging task to make your model, or to ensure your model, to force your model to learn the complex dependencies among the data. And so for like conventionally used mask language model, the task is fairly easy. So it's this kind of non-generative or easy mask language modeling objective will also hinder the predictive power of this of like ESM or like BERT model. And if you have like a generative model, you learn to generate the data from like completely noise, or you learn to recover noisy data at every noise level. This is a more challenging task, and you can learn better representation by doing these more challenging tasks. So it's kind of like a famous quote from Richard Feynman: "What you cannot create, you do not understand." You learn to you understand the data better by learning to create them. And yes, so this is the summarize of our protein mask language model. And for like autoregressive model, the autoregressive model perform reasonably at sequence generation, right? But it cannot do very better in like understanding sequences, including both NLP, natural languages, and proteins. This is because that the protein is a structural macromolecules. It's a spatial structure. It's a structured data, and it has no predefined order, for example, from left to right. And while this left to right autoregression is a very good inductive bias for natural languages, it's not necessarily a very good one for proteins, because we know that if we want to better learn the protein data, you need to like globally capture the residue-wise interaction and like coevolution. So this one unidirectional receptive field, you can only see the one-sided context, will make autoregressive model will make autoregressive model perform like not satisfactory in generation and in predictive tasks. So to summarize, what we need for a reasonable or best suited framework for like modeling protein sequences, we need there's two keys to achieve a like a general purpose or a more strong protein language model. The first one is a very strong and scalable generative modeling. You need to make the protein language model a generative one, and rather than a non-generative one. For example, BERT. And in such a way, you can best digest the universe of the massive protein sequence data. And the second one is that you need to ensure that the model has bidirectional or global receptive field for like better modeling the residue-wise global interaction inside the protein sequence data. And so you don't want to, as a result, you don't want to use like mask language modeling because it's non-generative. And you don't want to use autoregressive model because autoregressive model does not have like bidirectional receptive field. So what is the answer? So in our work, we propose to like to achieving this kind of unified protein language model by combining the language model and discrete diffusion. And so when you combine the language model and discrete diffusion, you can satisfy these two keys to this answer. You can have like scalable generated modeling, and you can also have like bidirectional receptive field for protein data. And so this is the overview of our work. And so we are building our model. We're building our language model based on discrete diffusion, and we pre-trained our discrete diffusion language model on a like evolutionary-scale sequence data. And after that, we can use our model to generate protein sequences. We can use our model to like to provide a better learned representation for like downstream tasks, and we can condition our model to generate correspond to multiple conditioning scenario to generate like a sequence for various needs. And to be more specific, our model in the paper we mainly focus on or investigated the absorbing discrete diffusion variants of discrete diffusion for our work, because it can because absorbing diffusion the noising process of absorbing diffusion is masking a proportion of the protein sequence data into like using mask token. So it can readily connect to the mask language model and autoregressive model. And we can and it can also be seen as a generalization of mask language model, and you can treat it as a mask language model that can generate. And but if you choose another kind of noising distribution, for example, the uniform distribution or other kind of distribution you can define, you can obtain other kind of discrete diffusion model. And we in our preliminary study we have tested like different kind of discrete diffusion, including like uniform or multinomial diffusion, and other kind of diffusion, and we find that the absorbing diffusion is the perform the best, and so we pay more attention on absorbing diffusion. And after pre-training, we can use our model to generate new sequences in a the reverse diffusion process is like it behave in a mask predicts approach. And first you need to design when generating, you first need to design a sequence length you want. For example, like 100 or like 200 or whatever number you want, and you will start from a 100% noisy states of this sequence filled with all masks up to this length, and then you iterative samples a less noisy states given the previous states using from this distribution, and which can be treated as like you predict you predict a clean data, that the model thinks is more clean, and you use this intermediate prediction, and you then remask this intermediate prediction of x0 to be a less noisy data. You can use a confidence-based remasking strategy. For example, you have like cross entropy or like log probability of your prediction of your prediction of each amino acid, and then you can use this log probability to choose you can choose to mask out the last several ones to be the mask states, and treat it as the current prediction of xt. And we can see that we do like several evaluation on our like unconditional generation, and we can see that for visualization, our model can generate like structurally plausible proteins from like 100 amino acids to like 1,000 amino acids. And to be more specific, we calculate or we measure the structurally plausibility using ESM-fold PLDT, and we also measure the structural novelty and diversity using like the PDD using the TM score to the most similar protein in the PDB datasets, and calculates diversity using the TM score between the pairwise candidates. The pairwise TM score inside the generates candidates, and we can find that our model can generate structural plausible proteins and with a reasonable diversity and novelty. And we can also find that after calculates the statistics of secondary structures, our model behave the generated samples of our model is similar. The statistics of our model is similar to the PDB, to the proteins in the PDB. And we also find that when you're scaling our model, you can better handle the longer proteins. For example, you can see that if we have only a 3-bit model can perform the best for all lengths. And we also investigated the we also like confirm our intuition that the diffusion model is the best suited framework to protein language modeling, which is better than like autoregressive language model in generation and better than mask language model in generation. And we need to highlight that for like autoregressive language model, you cannot easily determine the length of the sequence generated by the autoregressive model. But like for many cases, you didn't want the model to like generate arbitrarily length of the proteins. So I think this is another weakness of autoregressive protein language model. And like we also investigate how to train our model or how to establish our model. And because we observed some like unstable pre-training in the training dynamics of our model, and we try to like compare, or we try to introduce a two-stage curricular learning inspire strategy. And we first use mask language modeling to pre-train our model, or you can use like a pre-trained ESM tool to initialize our model, and then you use the diffusion objective to train the model. And as we can see from the figure in the right, this two-stage pre-training strategy can attain the best performance. But we can see that pre-training from scratch, directly from scratch, can attain a comparable performance. And we also like evaluate or showcase the representation learning power of our model, because our model is learned is learned at every noise level, including the 0% of noise. So when you like input takes the original amino acid sequence as input, you can use the last layer of hidden state or representation as the embedding of this sequence, and you then learn additionally like linear projection, or learn like classifier or regressor for various downstream tasks. And we show that our model can perform better than like mask language model because we are the diffusion language model is facing a more challenging task than mask language model, than simply mask language model. So it need to enforce the model to learn the complex dependencies inside the data, so it can better understand the data. And for like autoregressive model, it perform the worst in this kind of predictive tasks. And actually unconditional generation is not the ultimate goal for like generative model, because for like many downstream application, you need to like condition your constraints or condition your prior into the generative process to like satisfy your own desired. And we test and develop several like conditioning strategies for our diffusion protein language model. The first one is like sequence conditioning. This is very easy, and you don't need to like retrain our model. For example, like in the task of motif scaffolding, you can fix the motif sequence and generate the rest of the sequence for like scaffolding. And in this task, our model can attain a reasonable performance. and we compare our model to like we also compare our model to like RF diffusion, and we can we with some analysis we find that our model can like do some in some cases of focusing on more evolutionary conserved motif, our model can perform our model can perform better than RF diffusion, but like for more structural motif, it's more like a structural have more structural characteristics. RF diffusion, which can use the direct use or direct operates on the structure space, is the best tool for this kind of tasks. And we can also like conditioning our model. We also like we can also like condition our model to do some like cross modality generation. For example, for like inverse folding, you need to condition your model on a given protein structure, then generates protein sequences that can fold to this structure. And we follow our previous work, the idea to use a lightweight adapter, use adapter tuning, and combining with a additional modality encoder. For example, for this inverse folding, we use GVP transformer as the structure encoder, and and in this case we only chained the parameters of the adapter, so it's very like and the rest of the diffusion model, diffusion language model is frozen, so it's very lightweight and very efficiently a very efficiently paradigms. And we can find that our model using this diffusion protein language model as a training objective perform better than our previous work, the LM design, which used mask language model as the sequence decoder. And we measure we measure the performance in terms of like self-consistency TM score and the PLDT of ESM fold. And another thing I would like to mention is that because this kind of cross-model generation use adapter tuning, so we can have so the rest of the unconditional sequence model or unconditional language model is the same as before. So you can readily have like two models, a conditional model and an unconditional model. So you can readily use the strategy like classifier free guidance for free, and to balance the conditioning strengths to make the model like more to consider more from the conditional signal. And finally we did develop a like classifier guidance strategy to inference time conditioning. And for example, we can like chain we can additionally chain a like secondary structure prediction classifier, and we can use this classifier secondary structure classifier to like impose the gradient information during the generative process of our model to guide our model to like satisfy the targets of this model of this classifier. And you can see we showcase that when we like take as input we extract the secondary structure from a template protein. We can use our model with this classifier guidance methods to generate a new proteins that has very similar secondary structure annotation similar to the template proteins. Okay, so this is pretty much cover our work. And so some takeaway is that this is I think this is the first time a protein language model that can do both protein generation and providing protein sequence representation, or as an embedder. And for some like future direction, we can one of the most exciting thing is that how to develop a multimodal version of this protein foundation model, and to account for both protein sequence and protein structure. And there are some like some questions and so many people asking about a comparison between our model between our model and ESM. And so we highlight that our model is a generative one and ESM is a non-generative one, and it can be seen as a generative generalization of mask language model, for example, the ESM, and we can by nature generate samples. But for ESM, you need to like introduce some like Gibbs sampler or Monte Carlo method to sample from ESM. And another very related work is evoludiff. And evoludiff, so we differ from evoludiff in terms of like modeling. We use a more general absorbing discrete diffusion, and evoludiff use like a order agnostic autoregressive diffusion, and we use a transformer as the neural networks to better capture the structured data. And evoludiff use like MSA transformer or like convolutional neural network based model. And finally we empirically demonstrate our model can do some like representation learning and conditioning beyond like sequence conditioning. And also like for open source codes, yes, we are working on passing the company internal review for our codes, and the training and inference code will go public, and we welcome everyone to use our model. So yes, thank you. So I'm here to answer every questions as I can.
Yeah, anyone can feel free to either unmute and ask their questions or put it in the chat and I can read it out for you.
Hi, Zaixiang. Yeah, this is great work. Can you hear me? I don't know if I can be heard. Yes.
Yeah,
great.
yeah, I can hear you. Yeah.
Great. Yeah. Hi, my name is Pranam. A really great paper. One of my favorite papers of the year, I would say, in this space.
Thank you so much.
Great work. So I guess I have a few questions. One being, the reliance. The first question is very simple, right? The reliance on PLDT as a metric to. I mean, I know there's not many metrics that you can go off of tell you whether a protein is plausible, but we do know that there are a lot of realistic proteins that don't have high PLDTs, right? Like disordered proteins. And so when you're evaluating, like say, like your two-step model versus your fully pre-trained model, and you're using distribution of PLDT, have you investigated whether like those like other properties of the proteins that do have lower PLDTs and whether they could still be plausible? Because you may be just biasing the model towards structured proteins, which is only a very small percentage of the proteome.
Yeah. This is a very great questions, and we were asked by this question. We also raised by the reviewer during our submission, and yes, we have investigated the performance of our model for on like different proteins with different PLDTs, and for like so for the pseudo likelihood, we use like pseudo likelihood to evaluate the we sample a subset of like more structured proteins which have PLDT greater than like 80, and we sampled another set of low proteins with which is less structured with a probability less than like 50, and we find that the pseudo likelihood of these two data is similar, but yes, and it's similar, but our generation process seems, yeah, you're right. Our generation process seems to bias towards more structured proteins, and you can more easily or more likely to sample proteins with like more structural characteristic. And we guess that this is because that the data, the more structured data is more easily to learn, because from a probabilistic graphic model point of view, you use more structured data provide more statistical dependencies. For example, the coevolution or like physical interaction, and which is more common or more common pattern or more easily to learn pattern inside the larger amount of sequence data. But when you like for those lower PLDT data, it's kind of like more long-tailed patterns. So you need to so it's more challenging to learn, I think. So this is my random thoughts on this.
Yeah, and thanks so much. And just one quick question, because I know there's other questions, is maybe I just misunderstood. When you did the two-stage training and you trained with, you had a pre-trained ESM2 and then you did DPLM on top, is that, were you doing latent diffusion? Were you starting with ESM2? Were you starting with ESM2 embeddings and performing noising and denoising on those, or was that or was this a separate training procedure altogether?
We are not like those a latent diffusion very kind of stuff. Because so one thing I forget to talk about is that our model is identical in terms of like a model architecture and something like that is identical to ESM2 for like we want to do a fair comparison. So we can initialize our model from ESM2, the whole parameters, not only the embedding. So yes, so it's, you can see that as that a generated generalization of ESM2 is our model. So yes, so you can first use ESM2, which is essentially a mask range model, to initialize the model, and then you use diffusion to for the rest of pre-training. This will make the procedure much more easy. Yeah.
Great. Thank you so much.
Thank you. Thank you for your question. There are multiple questions in the. Do you have any figure on how inference speed for generation the approach to autoregressive model? I didn't have this inference speed, but right. So I didn't have this inference speed comparison, but what I can say is that we use like 500 iteration for our for generation, and for like and we find that if the performance, the PLDT in terms of PLDT will only slightly drop when you reduce the generative iteration to like 300. Yeah, but I didn't have a figure for comparison right now. Yeah, and we want to highlight that the inference speed is not the main focus of our work. The main focus of our work is to find a more suitable way to model the protein sequence data. Yeah. Did you test DPLM on some other mutational effects benchmark? No, we didn't. But for like protein gene, yes, we want to like test our model on this benchmark, but we didn't have a result right now. Yeah. If we have any updates, I will update the results on our archive version. Yeah. Can you elaborate more on the table about comparing performance of variable protein predictive downstream tasks? Okay, so like we used the benchmarks used in the Sapro paper, and they test the predictive task in these several, like for some is like for PPI prediction, or other kind, or other task is like functional prediction, and we also test a secondary structure prediction in the last column. And yes, and I have no idea if you were asking about the difference between these downstream tasks, or
Yes. Your talk, can you hear me?
Yeah.
Thank you for the I was wondering, so for those features, how you're like generating the proteins and compared, like how is the thermostability, for example, compared? Like
okay.
Okay,
so you are asking about the is this method comparable, or can this method be compared in these different tasks because they use different features?
Yeah.
Okay. So like I think this is the standard approach to test the like representation learning capability. You use the feature derived from your model, for example, different model. And for the STEM data set, for the STEM predictive downstream data sets, you train a linear classifier or regressor with like comparable or similar parameters and similar model architectures, and to predict this downstream task, to test the how informative your representation is from your model. So I think this is the standard approach, but I think your question is valid because this is like different kind of model, have like different model parameter size. I think there can be a more like reasonable or fair comparison approach, but we follow the previous approach, especially from like Sapro paper. Yeah.
I see. Thank you.
Thank you. Do you also use Uniref 50 also to train a bigger model? Isn't that database a bit too small? Yes, we didn't use like more sequence data beyond Uniref data sets, because we want to like have a fair comparison between our model and previous model, especially ESM2. And so, and yes, you can see that the performance of larger model, the improvement of scaling the model is like is not that much for like short proteins, but it's clear, the improvement or the gap is clear for like longer proteins. But I think this cannot answer the question about the size of data sets is reasonable. I think this can be a more empirical. There can be a more empirical answer to this question, because in the protein research community, there is no currently, to the best of my knowledge, I didn't know any study about the data scaling law of the protein language model. So yes, but use Uniref 15 is the reason to use this data size of data is for like fair comparison, and I agree that this kind of this size of data set can maybe a little bit too small. Yeah. Just curious if you compare your EC prediction performance against clean. No. Yes. Thank you for like bringing this approach to my attention, and I didn't compare with clean model, and I will like study or get into to have a check of this setting or the comparison. Yeah, I didn't do that before. Yeah. Will the proposed use case of DPLM be available in the open source repo that will be posted later? Yeah, yes. Everything will be like open sourced. Yeah, including including like different conditional usage. Can you elaborate on the trade-off inherent in removing sequence length from modeling? Removing sequence length from modeling tasks for many generative design tasks, the length is an important dimension to sample. I think this is a great question. I didn't consider this before, but removing the sequence length from the modeling task. Can you elaborate on like elaborate on for Jeff? Can you elaborate on this question? Because for example, is there any like other study to incorporate the sequence length into the modeling task? Is there any study or? Hi, Jeff. Okay, so I just skip this question and I will be back. I will answer the last question. How long a sequence can DPLM be used for generation? Notice it was getting worse in terms of PLDT when sequence length increased. How about binder generation in case of protein complexes? Okay, so for like the length of DPLM can generate, we in pre-training or in training our model, we cut off the training data by like 1,000 in terms of length. So I didn't test the length beyond 1,000, but I think for example in this figure, like for longer proteins is a more challenging scenario to like generate a model. So I think like for longer protein sequences beyond like 1,000 residues, it can be much more worse. This it's not only because you the nature of like longer protein is very hard to model. It's also because of you in training we didn't see this kind of data, and we didn't have any idea that if our model can generalize, can perform this length generalize. But I think there are several like methods can help our model to generalize to longer protein, because our model use like a transformer with rope with the rotatory relative precision embedding, and there are several they are very and the length generalization or length exposition is a very very hot topic in large language model, and maybe we can adopt some like this kind of extension of length of language models kind of work into our model, and to make our model can generates better for like long proteins. Okay. Yes. And another question is that how about the binder generation in case of protein complexes? And we didn't test the case for like protein complexes. And in our training data, we treat all the protein sequences as like as monomers, and we didn't explicitly distinguish the like different chains. But I think this is a interesting or like important future improvement of our model, because you want to like use a your model to like doing protein complexes learning, for example, learning their interactions, and or like doing this binder design. And I think they have multiple approach to do this. For example, you can like introduce like chain identity embedding, or you can just trying to like offset your precision embedding, for example, by 100 or by like 1000 to make the model think that this is like two chains. But we didn't test this kind of cases, and I think this is a very interesting direction. And why is the model learning better in terms of structure from sequence when compared to traditional ML? Or why is this model learning better in terms of structure from sequence? In terms of structure from sequence when compared to traditionally, because for like traditionally, like for traditional mask language model, you only task the model to predict like a very small percentage of the sequence, and this is slightly easy. So the model cannot. So the model is lazy in because you provide more observation part or more condition to do these tasks. So the model can be like a little bit lazy to capture the more complex dependencies or relationship between inside the protein sequences. This is my random thoughts, and or this is my opinion, or our intuition in developing diffusion based language model, because our diffusion model can like denoising all kind of noise level, so it's much more challenging. And in such a scenario, the model need to like use like attention or something like that to capture the residue-wise interaction or residue-wise statistical dependencies. And this residue-wise statistical dependencies corresponds to it essentially corresponds to the like structure, because you see in AlphaFold you use like pair representation or like distance map to predict the protein structure. So I think this is further verifies that diffusion-based language model is more suited for like modeling protein sequences, because protein is essentially a structure data. It's structured sequence. Yeah, I haven't seen any study evaluating generated lens from PLM, but for example, if you want to sample from yes, for like variant sequences generation, currently we our thought is that for like protein sequence from the same family, the length variation could be not that much. So you can simply emulating the length in a length intervals. But I think we can doing the variable length sequence generation by like using other kind of generative model. For example, can which can support like addition, deletion, and modification. Or you can use, for example, in machine translation, there has a like this insertion-based model called the Lorentzian transformer, which learns to like adds learns addition and deletion of sequence data. And there is also a diffusion version of the Lorentzian transformer called I didn't remember the name, but called it's from well, I didn't remember the name, but it has a Lorentzian transformer, diffusion version of Lorentzian transformer. I didn't remember the name, but it formulates this deletion addition operation as the diffusion process and denoising process, and learns as a diffusion model. And I think this can be a very interesting direction to extend our model to support variable length generation. And can you elaborate a bit more on adapter module? How do you use it to condition the generation? Yes. Yes. So yes. So we place the adapter on the top of our model. So it's on the very top of our model, and so it takes as inputs the sequence representation of current step, and it also has a close attention mechanism to attend or to fetch information from this modality encoder, for example, the structure encoder. So you can treat it like a translator or something like that, or a connector that transform structure information to bias the hidden representation of the language model. So it makes the hidden representation of the language model towards more like structure aware, something like that. Yeah, and we only like change the parameter of adapter, and this is a like close attention based. It's kind of like the close attention in like stable diffusion. Use close attention to attend external conditional signals. Yeah. Hopefully I can answer your questions. Yeah.
Okay, that was awesome. Thank you so much for taking the extra time to answer all of those questions. It seems like there's a lot of discussion here, so people can also reach out to the speaker and follow up offline as well, I think, if there are any other questions. Yeah, with that, the recording will be available online in the next week or so.
Thank you.
And
okay.
Yeah, look out for our next couple of talks coming up on Twitter and the website, and see everyone next time. Thank you.
Yeah, and see you everyone next time. Thank you for inviting me, and yeah, thank you.